In this project, I'm going to build an OLED display that can be controlled by mobile phones. We have a guest Wi-Fi system in our office that handles a large number of daily visitors. I noticed leaflets with the Wi-Fi password scattered throughout the office, so I decided to come up with a better approach. The goal is to have an electronic display in every conference room that can clearly display the Wi-Fi SSID, password, and Wi-Fi QR code. The display will also allow employees to send custom notifications. My videos are fast-paced, but all the code, notes, and images are posted on my website, along with any updates. The link is in the video description. In previous videos, I've written mobile phone apps or used existing apps to control my projects, but in this case, we'll keep it simple by using SMS text messaging for control and feedback. Communication flows from a mobile phone via SMS text message to a Twilio API function, which then fires a webhook on the Adafruit IO cloud service. A CircuitPython program running on an ESP32S2 Wi-Fi enabled board monitors the Adafruit IO feed using MQTT and then performs commands or displays any published messages on an OLED display. Adafruit IO is a paid service, but they do offer a free plan, which I'm currently using. Leveraging Adafruit IO saves me the trouble of spinning up and maintaining a web server and an MQTT broker. The setup is unbelievably easy. You just navigate to the Feeds tab, then click New Feed, then give it a name and a description. Then click Create. Afterwards, click on the newly created feed to open it. Now, scroll down and click on Webhooks. The default options are okay, so just click Create. Again, the defaults are fine, so just click Create. Here's the webhook URL, which will be used by Twilio. Copy it to the clipboard, or just save it for later. That takes care of the Adafruit IO setup. Twilio is a paid service, but they offer a free trial that gives you a small credit. I'm currently paying $1.15 US per month for a local phone number and around a penny per text send or receive, which includes a carrier fee and taxes. Still, your mileage may vary depending on your country and carrier. Twilio is a very robust system, but configuration was relatively easy because I'm only using a tiny subset of its functionality. After creating an account, you'll need to click Get a Twilio phone number. I got a 205 area code phone number. On the left sidebar, click Phone Numbers, Manage, Active Numbers. In theory, you could just add the Adafruit IO webhook address to your new Twilio phone number, and the Adafruit IO feed would start receiving text messages. Unfortunately, this currently doesn't work properly because Adafruit IO only supports JSON, and Twilio expects XML. Hopefully this will change in the future. However, it's not too difficult to remedy by implementing a Twilio service with a single Node.js function to process the webhook. Although first click Verified Caller IDs, you need to verify all phone numbers that will be allowed to receive text from your new phone number. It's a constraint set by the low-cost plan, but it's alright because we only have a few users. I've already added my 2 phone numbers when I registered. Now let's write the function. Click Explore Products, scroll down to the Developer Tools, and click Functions and Assets. You can then click the 3 dots next to the Functions tab to pin it to the sidebar for quicker access in the future. Click Create Service. I'll just call it SMS Display. Click Next, click Add, and add a function. Let's call it Process SMS. I'll go ahead and delete all the example code. And to save time, I'll paste in the Node.js function that I wrote. The function requires Axios, which is an HTTP client. So under Settings, click Dependencies. Under Module, type Axios. Leave the version blank for the newest and click Add. The next line declares a constant, max SMS, equal to 54, which is the maximum number of characters the text message can contain, which is dictated by the display and font size. Exports handler is an asynchronous function that will receive the SMS event and callback. The event contains data such as the sender phone number, the text message, and other metadata. Callback will be returned to Twilio. A message response is generated and called Twiml. An instance of Axios is created and passed the base URL for Adafruit IO. This is the first half of the Adafruit IO webhook URL, which is static. A try statement is used to catch any errors. The event body, which is the text message, is checked to make sure it doesn't exceed the maximum length. If it does, then a failure message is texted back to the sender, and the callback is returned, which ends the function. Next, an HTTP post is created and appended with the second half of the Adafruit IO webhook URL, which is the dynamic portion. I'll be changing it after the video goes online. A single value is posted, which contains the event body, in other words, the text message. If an error is caught, then a warning is texted back to the sender, and the callback is returned, which ends the function. Otherwise, a successful message received text is replied to the sender, and the function ends. A final error catch will log to the console and be returned to Twilio for debugging. Click Save to save the function. Afterwards, click Deploy All to deploy on Twilio. Make a note of the function address, which is located above the Deploy button. I'll copy it to the clipboard. It'll be combined with the function name to form the Twilio webhook address. Click the left arrow to return to the sidebar. Click on Active Numbers. Click the Twilio phone number. Then scroll down to the bottom. Under A Message Comes In, clear the existing webhook URL and paste the function address from the clipboard. Then type in Process SMS, which is the function name. OK, click Save, and that takes care of the Twilio setup. I'll go ahead and send a test text message to the Twilio phone number. Hello World is sent, and a message received confirmation is returned. Switching back to the Adafruit IO feed, the log shows the Hello World message. And this feed will basically be an MQTT broker. An Adafruit QtPy ESP32 S2 will be used to monitor the Adafruit feed over the web using MQTT. The QtPy is a low-cost board with a single-core 240 MHz Tensilica chip. It's Wi-Fi enabled, it supports I2S digital audio, has a built-in real-time clock, it's designed to run CircuitPython, and it has features such as ADC, PWM, SPI, I2C, a stemma plug, and much more, all in an extremely compact form factor. I broke the CircuitPython code up into 6 parts. We'll start with the MQTT Manager class, which is designed to reliably manage MQTT communications between the QtPy and Adafruit IO. The lower-level MQTT is handled by the Adafruit Mini MQTT library, which is imported as MQTT. From OS, getEnv is imported to provide access to environment variables, which is a new feature in CircuitPython 8, which I'll cover in more detail later. The constructor for the MQTT Manager class takes an MQTT client and a callback function onMessage. The MQTT client is saved. A variable AIO feed retrieves the Adafruit IO feed address from the environment variables. The onMessage callback is saved. An instance variable called status will track the MQTT connection status, and it defaults to disconnected. 4 callbacks are wired up to the MQTT client: connected, disconnected, message, and subscribed. The connected callback method is defined. It receives the MQTT client, user data, flags, and return code. Upon connection, status is changed to connected. The client subscribe method is called to subscribe to the specified Adafruit IO feed with QoS equal 1. MQTT provides 3 QoS or quality of service levels. Level 0 is basically no guarantee of delivery, sort of like the post office. Level 1 ensures that your message will be delivered at least once. Level 2 ensures that your message is delivered exactly once. Level 2 is currently not supported by Adafruit IO. The disconnected callback fires when the MQTT client is disconnected. The status is set to disconnected. The message callback is fired when a message is received. It relays the SMS message to the onMessage callback that was initially passed into the class. The subscribed callback is fired when the MQTT client successfully subscribes to a feed. Please note that there is currently a bug in the granted QoS level. If you set the MQTT client to QoS equals 2, then the granted QoS will also show 2, even though it's not supported and not actually running. A method called connect is used to connect the MQTT client to Adafruit IO. It'll only run if the status is disconnected to ensure multiple connections are not attempted. The status is changed to connecting. The actual connect command is wrapped in a try statement because Wi-Fi and internet connections are not always reliable. If the command is successful, then the connected callback above should fire. Otherwise, if an exception occurs, then the status is set back to disconnected. The loop method checks the MQTT broker for messages. It's wrapped in a try statement to catch errors. If the status is still connecting, then the method exits and returns false. If the status is disconnected, then the status is set to connecting and a reconnect will be initiated. Resubscribe to topics is false because the connect callback above handles subscriptions. If an error occurs, then the status is set back to disconnected. Either way, the method exits and returns false. Finally, MQTT client is connected is called to double check the connection, and if true, then the loop method is called, which checks for messages. Please note that the method is connected does not return false if you're not connected. Instead, it throws an error. I ran into a lot of MQTT and Adafruit IO reliability issues, and that's the main reason I wrote this class, in an attempt to make it more bulletproof. There are several possible errors that can manifest as either an MMQT exception or as an OS error. For the MMQTT exception, the method just returns false because it's probably just a networking issue that'll fix itself. However, the OS error usually indicates a more serious condition that requires a disconnect and reconnect to fix. A large 5.5-inch or 14-centimeter green 256 by 64 OLED module will be used for the display. The OLED display is very bright even in sunlit rooms and has a wide viewing angle. It can display 16 shades of green and is controlled by an SSD 1322 IC. It supports 8-bit parallel and 3 or 4 wire SPI communication. It's 3.3 volts, so it's easy to hook up to the QT Py. The OLED CS or chip select line is connected to the QT Py as A0. RST reset is connected to A1. DC data command is connected to A2. It doesn't really matter which pins are specified for CS, reset, and DC because they'll be specified in code. SCLK serial clock is connected to SCK. SDIN serial data in is connected to MOSI, master out slave in. VIN is connected to the QT Py's 3.3 volt line, and the grounds are connected. The OLED can draw a lot of current, which could brown out the QT Py. Therefore, a 100 mic capacitor is placed across the 3.3 volt rail and ground. In order to simplify the coding, I've broken the OLED display code into 4 separate classes: a clock, a disconnection notice, custom messages, and password info. I'll start with the disconnection layer because it's the simplest. A few required display I/O classes are imported. The disconnection class sole function is to display a disconnected icon on the OLED when the network connection drops. The class constructor takes a single parameter, which is the primary display I/O group. The group can hold tile grids, which are used to display graphics, text, and images. Adding or removing items from the group either displays them or hides them. A small 24 by 18 bit map, formatted to 4 bits per pixel, is loaded from flash storage using the on-disk bitmap method. A new tile grid is instantiated to hold the bitmap, and it's positioned in the lower right corner of the display. An instance variable visible is defined to track if the disconnection bitmap is displayed. There's a single property called visible, which defaults to false. The getter returns if the disconnected bitmap is visible, and the setter toggles the visibility by appending or removing the disconnected bitmap tile grid from the display I/O group. It's good to check that the tile grid is not already in the group before adding it, and that it's there before removing it. The clock layer is more complicated. There are several imports. Adafruit Date Time handles the manipulation of dates and times. Adafruit Display Text Label is used to draw text. Adafruit NTP is used to synchronize the real-time clock over the internet with an NTP server. Display I/O groups are used to hold text labels. GetEnv is used to retrieve the time zone environment variable. Socket pool is used by the NTP library for networking. RTC controls the ESP32's built-in real-time clock. Terminal I/O font is used for the clock text. 2 constants are declared. The color white will be used for the text, although on a green display that's just the brightest green. A tuple of months holds the abbreviated names for the months. The clock class will display the date and time on the OLED. It also manages the real-time clock and NTP synchronization. The clock class constructor takes the font, group, socket pool, and the display width and height. The 5 pass parameters are stored as instance variables. The visibility of the clock defaults to false. An instance variable offset will slightly shift the clock position to avoid OLED burn-in. Scale will control the size of the clock. It defaults to big. The real-time clock is instantiated. An instance variable last time will track the last displayed time to prevent unnecessary updates. A Boolean NTP up to date will track if the NTP synchronization is current. The method sync time is called to perform the initial NTP synchronization. A display I/O label is created to hold the time and date text. I'm using a label class even though it uses more memory than the bitmap label class because I found the bitmap label to have a very noticeable flicker which won't work for a clock that updates every minute. The method parseTime is called to retrieve, format, and display the clock. A method called placeClock is used to set the position of the clock. The visible property works the same as the disconnection layer. It returns if the clock is visible, or can set the visibility by adding or removing the clock label from the display I/O group. Offset returns and sets the horizontal offset of the clock. This will gradually shift the clock around to avoid OLED burn-in. PlaceClock is called after it's set to perform the actual move. Scale returns and sets the size of the clock. Currently only scale 1 and 2 are supported. Again, placeClock is called to update the display. The placeClock method sets the size and position of the clock. The XY label position is calculated based on the scale and offset. The smaller scale 1 clock is positioned in the right top corner when the Wi-Fi information is taking up most of the screen. The larger scale 2 clock is displayed in the center by itself. The isDST method checks if it's daylight savings, which varies by where you live. In most of North America, it starts on the second Sunday of March and ends on the first Sunday of November, which is relatively easy to calculate using these formulas. You'll need to modify this code if your city is different. Ideally, the Adafruit library will be upgraded to automatically handle DST, or even better, all of the world will stop using DST. The sync time method ensures that the real-time clock is accurate using networking time protocol. A try statement will catch any network errors. An NTP server is instantiated using the pass socket pool and the time zone offset, which is retrieved from the environment variables. The Adafruit NTP library currently doesn't automatically handle time zones, so you have to specify your offset in hours from Greenwich Mean Time. Unfortunately, the library doesn't account for daylight savings time yet either, so the current year, month, and day are passed to the isDST method. If it's daylight savings, then the NTP server is reinstantiated, but the time zone offset is modified by 1 hour to allow for DST. It has to be instantiated again because the current TZ offset property is not exposed by the Adafruit NTP library. Next, the real-time clock is set to the NTP date and time. The NTP up-to-date instance variable is set to true. If an exception occurs, then NTP up-to-date is set to false. The last method in the clock layer is parseTime, which retrieves and formats the date and time. First, it checks that the NTP is up to date. Otherwise, it calls sync time. The date time is retrieved from the real-time clock and stored in a variable t. A variable h stores the hour. I'll be using standard time as opposed to the return military time, so if the hour is greater or equal to 12, PM is selected. Otherwise, AM. Then 12 is subtracted from the hour if it's greater than 12. If the NTP server is not up to date, then the AM/PM is displayed in lowercase as a subtle cue that something may be wrong. A variable new time holds the formatted date and time. The OLED display is only updated if the new time is different from the last time, so it only has to update once a minute. The hour in military is returned, which can be used by the main program to handle scheduled events. In addition to displaying custom messages, a notification chime will also sound, which will require audio output. Currently, the QtPy ESP32S2 does not currently support the Audio I/O library or the Audio PWM I/O library. Therefore, I decided to use the same Adafruit I2S Amp that I used in my BLE restroom key tracker project. I'm using a PUI Audio 4-ohm 3-watt speaker. Wiring the amp requires a lot more connections than a simple analog output. Positive and negative speaker terminals are connected to the corresponding pins on the amp. LRC, or left-right frame clock, is connected to the QtPy's RX pin. BCLK, or bit clock input, is connected to TX. DIN, or data input, is connected to SCL. SD, shutdown, is connected to SDA. The grounds are connected, and VIN is connected to 5 volt to maximize the possible output volume. The gain pin is used to adjust the amp gain from 3 to 15 decibels. A 100k ohm resistor to ground sets the gain at 15 decibels. By the way, you can use any pins for LRC, BCLK, DIN, and SD because they're specified in the code. The message layer class displays text messages on the OLED along with the chime. BDF is used for the font, which affords access to lots of different fonts. A bitmap label is used because the message is only displayed once. Since there's no updating of the label, flicker won't be an issue and it'll use a little less memory. Although I found both labels to be inefficient. For example, every minute update to the clock uses over 6K of memory. It'll eventually be recovered by garbage collection, but when you have a big program that uses a lot of memory, it's not ideal. The displayed message can span multiple lines, so wrapped text to lines is also imported. The Audio Bus I/O class is for the I2S Amp. The Audio Core class is used to play a wave audio file, which stores a pleasant chime sound, as opposed to the shrill beeps of a piezo buzzer. Digital in-out and direction will be used to control the amp's shutdown pin. A display I/O group will hold the message label. Microcontroller pin is only imported for the typing of the pass parameters. Sleep is used for the message duration. The message class constructor is passed GPIO pins for the I2S, bitmap clock, word select, data, and amp enable. A BDF font is passed along with the display I/O group. The audio bus I2out is instantiated with the passed GPIO pins. Audio core is used to load a wave file of the chime bell. The shutdown pin is configured for the amp enable. This will let the program power down the amp to save electricity when it's not in use. It's set as an output and initially off. The font's stored, although it's probably not necessary. The group is stored. A bitmap label to hold the SMS message is instantiated with the font, single line spacing, and the coordinates are zeroed. The method showMessage will display the passed message on the OLED for the specified delay time. Only one message is allowed at a time, so the group is checked to make sure it doesn't already contain the message label. The message is formatted and is changed to an ampersand to save space. I might add more abbreviations later. Next, wrap text to lines is used to format the text so it spans multiple lines if necessary, with a maximum 21 characters per line. A list called prior state will hold all existing items from the display I/O group so the display can be returned to its previous state afterwards. The group is also cleared while the prior state is populated. Next, the message label is appended to the group, which displays it on the OLED. The I2S amp is enabled, and the notification chime is played through the speaker. Afterwards, the amp is disabled. The sleep method leaves the message on the screen for the specified delay time. Then the message is cleared by removing the message label from the group, which is then restored to its previous state. A dinit method is added so that the main program can clean up the I2S audio on exit. The password layer displays the SSID, password, and a Wi-Fi QR code. A BDF font will be used for the password text. Bitmap labels will hold the Wi-Fi password text and the SSID text. L and QR code are imported from Adafruit Mini QR to generate the Wi-Fi QR code. Bitmap, group, palette, and tile grid are imported from Display I/O to handle the above text and graphics. Get ENV is imported from OS to retrieve the Wi-Fi SSID and password. The terminal I/O font is used for the SSID label. Color constants white and black are defined, and the QR code border pixels is set to 2. The password class constructor is passed the fonts, the display I/O group, and the width and height of the display. The 5 passed parameters are stored as instance variables. Visible will handle the layer's visibility, and like the clock layer, an offset will be used to prevent OLED burn-in. A QR code is instantiated. The add data method is passed the necessary data for the Wi-Fi connection. The make method generates the QR code in memory. QR bitmap will be a graphical version of the QR matrix to display on the OLED. The bitmap width is stored. Scale fits the QR bitmap to the display. Position Y vertically centers the QR bitmap. A 2-color QR palette is defined, and pass the constants for black and white. A display I/O tile grid is instantiated to hold the QR bitmap. A display I/O label, Wi-Fi label, holds the SSID in the smaller font. A display I/O label, password label, holds the password text in the larger font. A static method, bitmap QR, generates the QR code bitmap. It's passed the QR matrix. It creates a new bitmap using the matrix dimensions along with the border pixels. Next, the method loops through the complete XY range of the matrix to build the bitmap pixel by pixel. The bitmap is returned. Like the other display layers, there's a visible property. The setter sets the visibility of the QR code, SSID label, and the password. If show is true, the 3 items are added to the group. Otherwise, the 3 items are removed from the group. The offset property is the same as the clock layer. It allows the program to horizontally shift the QR code, the SSID label, and the password text to avoid OLED burn-in. Finally, here's the main program. The Adafruit bitmap font library is imported for BDF fonts. The Adafruit mini MQTT library is imported for MQTT. The Adafruit SSD1322 library is imported for the SSD1322 OLED display. The required GPIO pins and SPI bus are imported from board. The display I/O library is imported for the display text and graphics. The GC garbage collection is imported to address some memory issues, no pun intended. The microcontroller library is imported to allow a hard reset. From OS, getenv is imported to access environment variables. Socket pool is for network sockets. SSL affords secure internet access. Supervisor is imported to allow a soft reset. Terminal I/O is used for its font. From time, sleep is imported. Wi-Fi provides Wi-Fi networking. My 4 display layer classes are imported for clock, disconnection, message, and password. Finally, my MQTT Manager is imported to manage MQTT. A client ID that is unique to each QtPy board is created by taking the least significant 19 bits of the microcontroller CPU UID. I ran into a strange bug with respect to running multiple QtPy boards on the same network. All the QtPy ESP32 boards default to the network hostname Espressive. For an unknown reason, this was intermittently causing the boards to disconnect and core crash. I don't know if it's specific to my ASUS router. However, after assigning unique host names, the crashing hasn't occurred. Also, unique names help to identify stuff when you're using networking tools. The display I/O release displays method is called to ensure any existing displays are released. The SPI, DC, CS, and reset pins are defined. The SPI bus for the display is instantiated and passed the necessary board parameters. The baud rate is set to what I would consider a conservative speed of 5 MHz to favor reliability. The OLED display is instantiated and passed the bus, the width, and the height. I also found it necessary to modify the default call start value to 112 for my particular display. This is supposed to be the index of the first visible display column. The display I/O group is defined. This is the group that all 4 display layers will use to display text and graphics. A small font is defined using terminal I/O font, and a large font is defined using the bitmap font load method, which is passed the path to the font file profont22.bdf. The function connect to Wi-Fi establishes a Wi-Fi connection. I'm using an env file to store my SSID and password, so CircuitPython should automatically connect to Wi-Fi. However, despite what the docs say, CircuitPython currently doesn't automatically reconnect if the connection is dropped. Hopefully this will change in the future. Therefore, the IPv4 address is checked, and if there isn't one, then that means that there is no Wi-Fi connection. The function will loop until an address is obtained. The Wi-Fi radio connect method is passed the SSID and password from the environment variables. As always with network operations, error catching is used. The function will repeat every 10 seconds until a Wi-Fi connection is established. At this point, the program checks for a Wi-Fi connection and calls the above connect to Wi-Fi function if necessary. The socket pool is defined, which will be used by the NTP and MQTT protocols. A clock layer is instantiated to handle the display of the clock. The disconnection layer is instantiated to handle the display of the disconnection error icon. The message layer is instantiated to handle display of SMS text messages. The password layer is instantiated to handle the display of the SSID, Wi-Fi password, and QR code. A callback function called message will fire when an SMS text message is received. The text is cleaned up for more flexibility with the commands. Any non-letters are removed, and the case is set to upper. Therefore, users don't have to worry about case, spaces, or dashes for commands. If clean text equals Wi-Fi, then clock scale is set to 1 to make room for the password layer, which is made visible. This shows the SSID, the password, and the QR code on the display. If clean text is off, then the password layer is turned off and the clock scale is made large to fill the display. The reset command will restart the QT board. I did run into some bugs with the Display I/O library, where after a few days artifacts started appearing on the screen. If it recurs, then anyone in the office can reset all the displays by texting reset. I may add more commands later on. The final else indicates the text message is not a command, so the message layer is enabled and pass the full text message along with the delay time of 10 seconds. An MQTT client is instantiated. If you don't pass a client ID, then one will automatically be generated. However, I found the connection to be more reliable by always specifying the same unique client ID per board. Therefore, I'm using the same one generated for the host name from the CPU ID. The broker address is retrieved along with the port number, the username, and the security key. The socket pool is passed, and SSL create default context is used to secure the internet communications. The MQTT Manager is instantiated and pass the MQTT client and the callback function to be fired when a message is received. The connect method is called to establish the MQTT connection with Adafruit IO. A variable last hour is set to -1. It's used to keep track of when the hour of the day changes. The clock layer is enabled, and display show is called to actually display the main group on the OLED. The main program loop is wrapped in a try to catch errors. It's an infinite while. The clock layer parse time method is called to update the time and date if necessary, and returns the current hour. If the hour doesn't equal the last hour, then hourly routines are performed. In order to mitigate bugs and improve reliability, a soft restart is performed using supervisor reload. It occurs once daily at midnight when the hour equals 0 and the last hour was 23. Otherwise, the last hour is updated to the current hour. The available memory is printed to the REPL to check for memory leaks. Every hour, the password layer offset is cycled through one of 4 positions to reduce OLED burn-in. The clock layer offset is also adjusted plus or minus up to 12 pixels from noon. Our business hours are typically 5 a.m. to 5 p.m., so the password layer is automatically hidden outside these times in case someone forgets to turn it off. The OLED is given a rest between 9 p.m. and 5 a.m. Next, the Wi-Fi connection is checked using the IPv4 address. If the Wi-Fi is dropped, the MQTT Manager status is set to disconnected. The disconnection layer is made visible to show the error icon, and the connect Wi-Fi function is called. Afterwards, the loop is restarted. Otherwise, the MQTT Manager loop method is called to check for text messages. If true is returned, then everything worked, and the disconnection layer can be hidden if necessary. I did find it necessary to use GC collect to force the Python garbage collection each loop because I ran into memory issues with Display I/O. Hopefully these will get better as CircuitPython continues to mature. The loop sleeps for 1 second and repeats. An accept statement is added to catch Control-C and gracefully exit by putting the display to sleep, releasing Display I/O, and deinitializing the MQTT client, the message layer, and the SPI bus. That takes care of all the code. Here are the environment variables used in this tutorial. When you specify the Wi-Fi SSID and password, CircuitPython will connect to the Wi-Fi automatically on boot. The Adafruit IO username, security key, feed, broker address, and port are all stored here. Time zone is the offset from GMT. -5 is the US East Coast. CircuitPython 8 introduced support for environment variables. Environment variables are commonly used to store secrets such as passwords and API keys. This method does not make them secure, it only separates them from the code, so be careful not to post them to a public website such as GitHub. Don't worry, I'm going to change my Wi-Fi password, change my Twilio phone number, and regenerate my Adafruit IO key after this tutorial. The Adafruit IO key is obtained by clicking the yellow icon at the top right corner. It can be regenerated for security. I need to build at least 4 displays, and I wanted something that would look good in our conference rooms. I found an inexpensive aluminum case at my favorite electronics surplus store, All Electronics. The case didn't come with end covers, so I designed a pair in SketchUp and 3D printed them. I need to make some cuts in the aluminum case to mount the LCD display. The aluminum case has a concave back, which is hard to clamp down on the bench, so I cut a pocket in a scrap 2x4 with my Romex HS1 to hold it securely. I designed the holding jig along with the other holes and cuts in VCarve Pro, so no measurements are necessary. Just drop it in and cut. It's a very tight fit. Might be a little tough to remove. The first cut is a rounded rectangle to allow the wiring header on the back of the OLED to pass through into the enclosure. Next, 4 holes are cut for the display mounting holes. Here's the final results cut with CNC accuracy. I'm also using the CNC to cut out transparent green plexiglass covers for the 4 displays, and cutting the 4 holes that match the enclosure and the OLED mounts. It's hard to cut plexiglass by hand, so the CNC is a great solution, and it allows me to give the covers a very smooth, rounded corner. Okay, 4 identical covers ready to go. In order to keep the wiring tidy, I designed a PCB in Eagle to hold the QT Py, the I2S Amp, and the necessary connectors. Since I needed 4 PCBs, I ordered them online from one of the popular PCB makers to save time instead of etching them myself. The PCBs look great. I probably should do this more often. Much better than what I could do myself, and the silkscreen's a nice touch. I'll solder 7-pin female socket headers to hold both the QT Py and the I2S Amp. This way the boards can easily be removed, which is very helpful for debugging. One tip for when you're soldering headers is just to do the middle one first, and then check afterwards that everything is seated properly. If not, it's much easier to fix now than when all the pins are soldered. And once you have one pin soldered, it can be clamped in any position without the components falling out. Next, the 100 mic capacitor is added. It's temporarily held in place with some masking tape. I'm careful to align the negative end appropriately. It slightly overlaps the QT Py, but it doesn't matter because it actually fits underneath. The OLED display is connected with 3-pin and 4-pin JST-XH connectors. I went with 2 connectors because I didn't have any 7-pin versions. The male sides can only fit in one way, so there's no way to plug them in wrong. I'm not going to use the black screw terminal that came with the I2S Amp board. Instead, I'll go with a pluggable version. This will make assembly and disassembly quicker, and once the speaker wires are connected, no tools will be required to insert or remove the board. The terminal block plug just snaps in and out. Okay, I'll go ahead and plug in the QT Py and the I2S Amp. I omitted the gain resistor because the default 9 decibels was more than loud enough. It's convenient how everything just plugs together without any wires. Here's the aluminum case with 3D printed black end covers. They're friction fit, so they just snap in and out. The one on the right has 4 holes which will be used to mount the speaker. 4 black anodized M3 by 10mm screws, along with 4 nuts, will hold the speaker in place. The G on the end cover is for our company, and it acts as a speaker grill. Next, the speaker wires are screwed into the terminal block plug. I'm careful to match the positive and negative wires with their corresponding terminals on the I2S Amp. The mounting of the I2S Amp is currently not supported properly. The 7-pin connector could break if I leave it like this. I 3D printed 2 standoffs to better support the board. They're just held in with friction. I found a free OpenSCAD customizable standoff generator on Thingiverse that makes it super easy to 3D print any size standoff. The I2S Amp is much more secure with the standoffs, and since they're not screwed in, it'll still be easy to remove the board. Inserting the plug is much easier now since I can push down on the board. Here's the green OLED display. I ordered the module as opposed to just getting the display with a ribbon cable. The module handles the communication and provides a 2.54mm header for easy connection. I crimped together a wiring harness using 3 and 4-pin male JST-XH connectors from my custom PCB and a 14-pin female pin header that plugs into the back of the OLED display. I bought a 4-wire panel mount USB Type-C connector on AliExpress because it's the only one I could find that would fit in a 1/2-inch 12.7mm opening in the back of the enclosure. I designed and 3D printed a grommet to hold the USB jack snugly in the case hole. In retrospect, the USB jack was a bad choice because it's not fully compatible. It doesn't work if I plug it into a Type-C jack on a computer. However, it does work if I plug it into a Type-A jack using a USB-C to USB-A cable. I did try all the different resistor combinations on the male plug, but I couldn't find a compatible combination. In future projects, I would just buy a very short USB-C extension cable and either 3D print or CNC a panel mount for it. Alternatively, I could have just run a USB cable out the back with a strain relief grommet. I'll peel back the protective plastic on the plexiglass cover so I can insert the screws. I'm using M3 x 20mm green anodized aluminum socket cap screws. Folding the plastic back will hold the screws in place while I assemble the device. The plastic is fully removed from the other side. M3 by 3mm green anodized spacers are inserted to hold the cover above the display. I had to file down 2 of the spacers because the holes on the OLED were a little too close to the frame. The plastic is removed from the OLED. The display is sprayed with compressed air to remove any dust before the cover is put on. The CNC cut holes line up perfectly with the OLED holes. 4 more M3 by 3mm spacers are placed over the screws. This will prevent the components on the back of the OLED from coming into contact with the aluminum case and possibly shorting out. The other end of the OLED wiring harness is fed through the rectangular cutout in the aluminum case. Now the display is attached to the case. The green screws go through the plexiglass cover, through the OLED, and into the aluminum case. They'll be held in place by M3 nuts. The 2 OLED plugs are plugged into my custom PCB. The USB plug is plugged into the QT Py. The screws on the side of the case will also hold the custom PCB in place. M3 by 3mm PVC spacers are placed on the screws to hold them in place and to ensure the bottom of the PCB doesn't short out on the aluminum case. Off camera, I added M3 nuts which keep everything together. That takes care of all the hardware. The end cover can be snapped into place and the plastic protector can be removed. Here's the finished product. Well, at least one of 4. Off camera, I added some rubber feet to the bottom. Here's the SMS display in a conference room. The OLED looks great. Any flicker is due to the camera. I'll go ahead and dictate a text message. Red team, please come to the 68th floor conference room. Click send. Message received. And the message is displayed on the OLED along with the audio chime. Next I'll type Wi-Fi. Click send. Faster that time. The Wi-Fi information is displayed on the screen. I'll go ahead and scan the QR code. The connection is very fast, so I'll pause the video. Now guests can log onto our Wi-Fi with just a single button press. I hope you like this project. You can support this channel by subscribing, leaving a like, and sharing. Thanks for watching.